I want to talk about where tanning is going, where it can go, where it might go, where it probably should go. We need to start from the point of view that we're in business to stabilise collagen, and that's the basis of our industry. It's also the basis of other industries that use collagenic biomaterials. However, the current paradigm doesn't work. What we understand, and by we I mean you, understand, and what I mean by you understand is what you have received as wisdom is demonstrably wrong. I'm going to give you an alternative view. We start with hydrothermal stability. It's a reflection of what we've done to the collagen in order to stabilize it, and it's normally reflected in the shrinking reaction. Fundamentally, it's a breakdown of the hydrogen bonding in the triple helix, which allows the triple helix to come apart, and we observe this as physical shrinking. And a good starting point is the model that was created by Helen Berman. As we can see here, we have a model triple helix. You can see on the left we have the bare triple helix, and the blue balls represent the buildup of water nucleated on the hydroxyproline. And you can think of this as the way that leather is structured. If you look particularly at the two right-hand triple helices, imagine them coming a little closer together, and you build up a structure between the triple helices. So now I'm going to use the terrible T word, theory. And what I want to talk about is a new view of the mechanism that I've termed link-lock. This is actually the culmination of thinking that started as far back as Graham Lampard's doctoral studies. And we can think about the stabilizing matrix being based on water, and we modify that matrix by the tanning agents that we introduce. Most tanning agents, and you can probably name a dozen without even thinking about it, will raise the shrinkage temperature to that sort of range. Pretty much everything will do it, with a few exceptions. The actual value that you get is determined by the entropy of the disordering reaction, the entropy of the breakdown of the collagen triple helix, and as we'll see, the breakdown of the intervening matrix. And surprisingly, the shrinking process is relatively independent of the linking chemistry. So all those chemistries, the dozen chemistries that you just thought of that give you that range of shrinkage temperatures, are all probably very different in chemistry, but they give you the same result. Let me give you an interesting example. Oxazolidine, sort of thing that we might be using instead of aldehydes in the future. This is from Descoup's work. Two reagents, same chemistry, one monofunctional, one bifunctional. Therefore, one is incapable of cross-linking, but the other one could. They give similar shrinkage temperatures. So, cross-linking, what cross-linking? Essentially, we must view tanning as a two-part process. The first part, the linking, is done by pretty much any reagent. It's a local effect. It's the binding of a reagent onto the collagen side chains. And all reagents will do this. Literally all reagents with greater or lesser extent. The lock part is the important one if you want higher hydrothermal stability, because the locking action applies to the linking agent, and not all reagents are capable of doing this. So what we see as the basis of shrinking is the breakdown of the intervening matrix, which then allows the unraveling. So shrinkage temperature is merely a reflection of how easy or difficult it is for the collagen to unravel into the space between the triple helices. If we have the two-stage reaction, if we have the locking applied to the linking, then the supramolecular matrix acts as though it was a single compound, therefore much more stable, therefore much more resistant to heat, therefore higher shrinkage temperatures. And what that means is that high hydrothermal stability is derived from the same mechanism, however you got it in the first place. So, let's have a look at chrome tanning and see where we might take this idea. Well, the linking agent is the chromium molecular ion. We start off with the dichromium species, 33 basic. Once we've basified it, it's a linear tetrachromium species, but it is bound covalently to the carboxyl groups of the collagen. The locking agent is the counter ion. If you use sulfate, which of course is the preferred reagent in industry, then you get high shrinkage temperature because it's a powerful locking agent. If you use chromium chloride and you process in exactly the same way, you get a shrinkage temperature of 85. But then if you put sulfate in, shrinkage temperature goes up to where you expect it to be at 110, 115 degrees. That's a model of how it works. The sulfate acts as the locking agent between the chromium species, but it operates via the aqua ligands. It gets no closer. Those models that you've seen where you've got sulfate linking to chromiums does not happen. The X-ray studies that we did some years ago showed that unequivocally. The sulfur gets no closer than that, and it may even go away. So, the counter ion is the key to chrome tanning success. And actually there are other counter ions that are even more effective. Pyromelitate, a tetracarboxy benzene compound, will push the shrinkage temperature of chrome tan leather up to 130 degrees. So, if the view that you probably have received in your training, your education, is right, then there would be no role for the counter ion. The tanning would be independent of the counter ion. It wouldn't matter whether you use sulfate, chloride, perchlorate, nitrate, whatever. But that's not the case. It's highly dependent on the nature of the counter ion. Therefore, your conventional cross-linking model cannot be right. But we can explain all the observations if we use the matrix model. Let's have a look at masking. So we have a conventional definition. We think about masking works by reducing the chrome reactivity by using up reaction sites. The one thing we should bear in mind is that if you put a masking agent in with your tannage, perhaps including it as formate or formic acid in the pickle, the masking reaction proceeds the same rate as the tanning reaction. So it actually doesn't constitute, at the beginning, a masked tannage. But probably what you haven't appreciated is that masking can mean either reducing the reactivity or increasing the reactivity. And depending on which masking agent you use, you will likely get a different outcome. Let's take some work from Holland, along those 1940. Here you have comparison of the chrome content of wet glue masked in different ways. There you have formate as the typical masking agent, but that looks to me like an increase in reactivity rather than a decrease in reactivity. We could talk about these other ones a little more, but we'll leave that to one side. Oh, just to let you know, that's reasonable sort of industrial type offer format. The difference is in what the masking agent presents to the outside world in terms of, does it make the chrome complex more hydrophilic or more hydrophobic? And here you see the difference between oxalate and formate, where oxalate is presenting groups that are clearly capable of powerful hydrogen bonded interaction with solution, therefore it's hydrophilic, therefore it's simply blocking reaction sites, therefore making the chrome less reactive. In the other case, we have formate, which presents a hydrophobic group to the environment, makes the complex more hydrophobic, and therefore would prefer to be in the environment of the collagen than in the hydrophilic environment of the solution. Therefore, it's more reactive. So, your masking effect is a competition between increase in hydrophobicity and decrease in complexation sites. And it depends on the nature of the masking agent and then actually how much you use as to what the overall outcome is going to be. And one thing that we need to keep in mind all the time is that unless we've prepared the complex before we start, that masking effect is changing all the time. It's a dynamic process, and of course, that's got to be exploited. This demonstrates the difference between what we actually get, what we prefer, and what we assume is the case. Here you see the preferred effect is for the chrome to become increasingly reactive. That's why we basify, we make the system more reactive. We assume that what we're getting is a gradual decrease in the reactivity. But what we're actually getting, typically if we're using formate, is an increase in reactivity and then a decrease, which is pretty much exactly what we don't want. So, deal with it. Considering where tanning is going, what about alternatives to chromium? We're constantly under pressure about discharging chromium. What have we got? Any options? No, there's nothing. All metals will act as a linking agent. They may even act as a locking agent in playing a role in the semi-metal tan, but that's pretty specialized. There are no other candidate metals that are capable of creating that covalent link. And that strong initial linking reaction is important in creating high hydrothermal stability. And the effectiveness that you get does depend on exactly how it interacts, and most of them tend to interact electrostatically, a weak interaction, and therefore at the heart of a weak overall tanning effect. You can improve matters, you can improve the binding of the metal to the collagen. Jeremy Holmes showed this. If you graft on chelating groups, then you can push the shrinkage temperature of aluminium tannage up to 95. But it's complex chemistry, and it's not really likely to be introduced commercially. You can use all metals mixable with chrome, but there's no advantage really. Well, possibly getting some enhanced reactivity using aluminium, You also get the same effect with titanium. But the more you put in, the worse the outcome is in terms of hydrothermal stability. And of course, the more you put in, the more you introduce the character of that particular metal, usually in terms of hydrophilicity, usually in terms of increased cationic character. So, what are the options for organic tanning? Well, we can get a strong interaction with collagen from many organic reagents, but they will only act as linking agents. But what is interesting is if we look at the options for new organic chemistries, then there's the potential for new locking reactions. Because if we have new chemical sites, there are new and alternative chemical reactions that we can exploit. If we start with the traditional materials, the veg tans, we're interested primarily in the condensed tannins, and there are 4 basic types that we typically come across. Procyanidins, top left, are the most common. Quebracho type reagents are essentially procyanidin. Occasionally you come across prodelphinidin. The other 2, the profacetinidin and the prorobinatinidins, much less common, but you'd know those 2 in mimosa. We can model the effects of locking those reagents by considering the various, the 2 ends, the A ring and the B ring, which are either chlorobutadiol or isosanol or paragalol catechol. It was originally Simon Phillips who looked at the way in which these polyphenols might be used in tanning, and he used formaldehyde to cross-link. Here, Li Jiang Song recently looked at the kinetics to measure the affinity of those particular phenols for cross-linking aldehydic agents. Formaldehyde, of course, we're not likely to use, but it's there for comparison purposes. And what we can see is that not all aldehydic agents react effectively. We want a fluoroglucinol A ring, so that means the procyanidins and the prodelphinidins. And the preferred B rings are the prodelphinidins and prorobinatinidins, that is 3 hydroxy groups on that right-hand ring. We don't actually need to use veg tans. If we use monomeric veg tans, actually they work just as well, and of course you don't have the problems of stringency and penetration. So, use the non-tans in this context. So, ideally we want prodelphinidins for organic tanning of the future, except there aren't many available. I'll give you 3. Myrica esculenta, which is polymeric. Pecan pip, it's also polymeric. Or you can use green tea. Green tea is a very good tanning agent. So, unfortunately, the Chinese prefer to drink it. What about other interesting things? Naphthalene diols don't look terribly reactive, and in fact by themselves they really don't function very well as tanning agents at all. But if we use a locking agent like oxazolidine, well, obviously nothing much happening there. Slightly better, but we're still in that typical range. Slightly improved. Bingo. Use that dihydroxyphenol with oxazolidine, shrinks temperature 110. It's an option for the future. What else have we got? Well, some materials have been around for a while. Dialdehyde carbohydrates we're familiar with, either made from starch or dextrin. We might think of doing the same kind of ring opening reaction to hyaluronic acid, calculate how much hyaluronic acid you discharge from your tanneries annually. It's a huge amount, 0.3% in hive. And it could be the basis for hypoallergenic leather. Again, linking agent, but all sorts of options for locking. For the carboxyl group, you could lock it with chromium. Maillard reactions have been around for a long time using reducing sugars. Again, this is your linking agent, but plenty of options for locking. How about something different? This is an example of a bog body, pretty common in North Europe, and of course the assumption is that this guy is veg tanned. But actually he's not. Peat bog chemistry is much more complicated. And what you have here is two reactions. One using this 5-position hexoxyhyaluronic acid, and that's actually this bit here. So that will interact directly with glycosylamine, with the guanidino group of arginine in collagen, and give you a glycosylamine. An alternative is to go down this route where this hyaluronic acid derivative will actually break down and form something that resembles an anhydrin, which you probably know as an analyzing compound of amino acids, gives you that pink color. So, this is based on the breakdown product of plant cell walls, but it gives you an option for locking reactions. We have nordihydroguairitic acid, which we can extract from the creosote bush, which can be polymerized by oxidative coupling. It will have a multiple interaction. The shrinkage temperature is only that of a linking agent, but you've got a possibility of locking. This has the interesting property of actually increasing leather strength, whereas all other reagents typically will reduce the strength. Here you have the option of increasing the strength. More complex chemistry from the iridoids. Genopin is fairly well known, but it does have the disadvantage that it turns everything really bright, dark blue. Or more recently, there's been some work done on europin, which is extractable from olive waste in privet. This is in fact a secoiridoid glycoside. You see at the top there's a GLC, it's got a carbohydrate group which you knock off, open the ring up, and multiple interactions, but it's still a linking agent. Just to make a comparison from Paul Rantune's work on reconstituted collagen films, you can see it works as well as glutaraldehyde. But of course, it's not an aldehyde. Well, it's not called an aldehyde. What else have we got? Well, we've got other options that we can take from reactive dye chemistry. These are the bits that create the covalent link of the dye onto collagen. And there's these heterocycles that are well known. And there's this kind of chemistry, vinyl sulfone, the amine ring, acryloyl groups. These will all create covalent links, and therefore can be the basis for a powerful link reaction, which we can then supplement with a lock reaction. So what are the options for the future? Well, we can play around with the counter ion in chrome tanning. That wouldn't be a bad thing if we could get away from sulfate. After all, it does have a very powerful effect on dissolving concrete. We can rethink the masking technologies for chrome tanning. We can look for other organic reagents. Single components are only going to give us simple tannages, low shrinkage temperatures. But it's clear that the options that are available for making hydrothermally stable leather are huge. It's not particular chemistries that will give you high hydrothermal stability. It's a general reaction. You just need to conform to the rules of lick rock. The matrix model allows us to think again about compact processing. These are the process steps of the future. Contract the processes. Do more than one thing at the same time. There are plenty of examples already out there. For example, binding dye onto beige tan is standard technology. And there are other examples like retanning and fat liquoring with the Roman house acrylate products. And you never know, it may be possible to get a single-step polymerization tannage, but right now I can't think of how you might do that. So, what do I conclude? The new mechanism is simpler. It's simpler than the traditional view of tanning. It's more elegant, it's more powerful. And if it's more elegant and more powerful, then it's likely to be closer to the truth. And if you think of tanning in that way, then the options for building in all sorts of properties now become clearer. For example, to make biodegradable leather would be one possibility. So, then, I would say this, wouldn't I? Review technology. But that's the way to make progress. And if you'll indulge me for a moment, my personal future, I'm going to retire soon. I've had just over 30 years in the industry. So this has been my SLTC swan song. It's been my last public lecture that's been scheduled. In fact, I calculated the other day that this is actually my 50th public lecture. So I just want to take a moment to acknowledge all my friends and colleagues in the UK industry. It has been a privilege and a pleasure to be part of the global industry. Thank you, and goodbye.